Project 3.6, the ACES Scratch Tester. This here is the final version of the ACES Scratch Tester and the prototype version. This is a project designed to be a module on a greater materials engineering lab. You can see here the main body with our PCB, our battery source, which is actually limiting this final design and is why it isn't working right now, but I'll explain that later. The camera, a motor driver, and of course our servo here, which is going to scratch a new development material. The idea is to test adhesion of that material, generally a powder on a surface. So let's see how this will be done. So we have a working prototype here, and the idea is we want to test how strongly a powder or a new material is going to stick onto a surface. So say we have a sample here. This would be a part of a greater module. So we would be having the X and Y coordinates set for us. We just have to determine the X. So say we set down on the sample, and the servo motor would be on here. There's a force sensor which starts it all in the servo motor, in the arm of the servo. So when we press down, which is saying that we are on the sample, that servo arm right there is going to swing. So if you press down, it's going to swing. Then we press down with this component onto the sample, and we're going to go up so that I can move onto the next sample. Let's take a look at how this is actually done and walk through the prototype. So it all starts off with the force sensor here. This force sensor here is like any variable resistor, similar to an LDR, where it provides variable resistance depending on the size of the force. The force is sensed on this front metal plate, and it is sent to our nano, which then sends out the signal to the servo. This is a 4-pin servo. Right here, we have our ground and our power, and then our white data line and our green feedback line. So if we set the servo, if we unplug it, set the servo to an undesirable position, our feedback line will allow us to make sure it is always righted. This also improves accuracy for a self-run materials engineering lab, which is very important. So the force sensor is inside the tip of the arm, which is attached to the servo. You can see here the black dot is the back panel of the force sensor. The scratch testing tip is pushed into that. Now there are threads around it so that I can screw in, but there's slightly enough space to allow it so that when it presses in, there's enough wiggle room to push into the force sensor. So the first part of this process is the force sensor. Once the force sensor is sensed to pressure, it's going to sweep out that servo arm. The force sensor sensing down means that it's on the subject, and so we want to scratch it. We go 0 to 180 and 180 to 0. We swing through, and then we want to ensure that we're on sample. So we press down, controlling the Z with this threaded rod. This needs a DC motor driver, which is necessary because the threaded rod needs to go up and down. So we need to reverse the polarity of the leads. This is done with the motor driver. Once we ensure that we've pressed down the subject and we've scratched it, we then want to go up the threaded rod to ensure that it can be moved on to the next sample easily. Before it's moved on, we take an image with this camera here, the OV7670. And this is a camera. It has a max resolution of about 640 by 480, I believe, pixels. And while it isn't the most accurate, it can get the job done. So let's look at the final design elements. This is the main body of the final design. You can see the center hole here is where it would attach to the OpenTron's arm, which is an open source arm that can control X, Y, and Z across a plane or an area. This cross-sectional here ensures that it's balanced with the battery pack being on Velcro so that there's easier removal. And the PCB and camera modules are screwed in with M3 fasteners. And then they're connected with a header through the pin as well. The motor driver is here on the side, and that is all our components for the main body. Then from under, the motor would stick on as such, and we have our connector here for the motor with our threaded rod and our panel. The servo would sit on the back of this 3D printed panel, which just sits on a copper nut with, again, M3 fasteners. this back pillow nut, I believe it's called, ensures that it does not roll off. Now the servo would be on here so that we can control the Z distance of the servo. The servo is attached to the arm here. There's a custom hole to fit tight, and then it's also glued in, so that's very secure. If we try to pull it out, it's not going anywhere. The servo arm, in turn, has a hollow inside where the force sensor is, and then also a hole out here so that we can see the flexible wires of the force sensor are coming out here. We can access those. As I mentioned before, these are threaded so that they can easily screw into one another. Finally, this project was going to include a metal tip, but unfortunately that fell through. So instead we decided to go with electroplating. That is the process of putting a thin layer of a metal onto another substance to give it those properties. In this case, it's graphite, and it makes this PLA a little bit more resistant, durable, and less reactive, which is essential for materials engineering. That is all for this project. I hope you enjoyed. Thank you, and have a great day.